The air conditioning paradox presents one of the most difficult challenges regarding climate change. As the temperature of the world increases, the need for cooling systems increase, not just so you can have a nice cold drink in your fridge, but for bigger industries like healthcare and food. However, air conditioning systems are also one of the biggest contributors to climate change and global warming. Therefore, ensuring these systems work as efficiently as possible is more imperative than ever. The compressor is one of the most vital components that impact the performance of a cooling system. This thesis explores the optimization process of a novel centrifugal compressor design and further investigates the methods with which are used to design centrifugal impeller blades. There are a variety of different design approaches for impeller blades in centrifugal compressors. Some focus around varying the geometry, whereas others use formula-based relations, for example flow path calculations, to determine the size of the blade. However, very few encompass a mixture of such methods. My research aims to develop optimal centrifugal compressor blade designs using computational fluid dynamics simulation results collected together in a populated database. The database contains the parameterized geometry of the impeller blade, including all dimensions that define the shape of the blade, with additional variables of operational speed, inlet pressure, fluid flow rate, efficiency, power required, and outlet pressure. Multivariate statistical analysis is used on the database, treating the parameterized geometry, fluid flow rate, and operational speed as inputs, and efficiency, power required, and outlet pressure as desired outputs. Multiple regression analysis has a capacity to generate prediction equations that link the input variables to the desired outputs. The graph you see on the slide is an example of the predicted equation for power compared to the original simulated power required value. Specific details have been removed from the y-axis for confidentiality. As you can see, the predicted values shown in lilac demonstrate good agreement with the original simulated values shown in black. Statistically speaking, this prediction equation for power required has an R-squared value of 89.35%. The prediction equations for efficiency and output pressure are also just as significant, with R-squared values of 87.89% and 90.24% respectively. Prediction equations such as these not only highlight the key geometrical parameters that have the greatest impact on the performance of an impeller blade, but also provide insight into how adjusting certain parameters can achieve a desired result. This has significant relevance when considering the design method of an impeller blade. Utilizing these prediction equations have the potential to guide optimal impeller designs for a range of different requirements, thus producing efficient designs and reducing CO2 emissions without the need to run multiple computationally expensive simulations.